All right. So for those of you who were in Bellevue, we had a pretty interesting panel on 40 gig and 100 gig and some of the work going on there in the standards bodies. And I thought it would be a good follow-on to continue with another panel talking about some of the optical developments going on in research work in that world, in that space, if you will. And some of you may not know it, but Drew's company, Drew Perkins from Infinera here, they started working on their stuff quite a long time ago, right about the time the bottom fell out of the industry, if I'm not mistaken. And they actually made it through, and they got their box to market, and they're doing quite well. What's kind of cool about that is there was a lot of work going on in the optical space prior to that. And when the bottom fell out, all of that cool work going on stopped happening. And now things are slowly starting to pick back up, and some of that work's starting to get engaged again and come to fruition for us, and hopefully we'll see some more cool stuff coming down the pike here soon. Why it's important in the internet space and the IP space is it gives us some really cool new tools and ways to move more bits more efficiently, better spectral efficiency, if you will, some people like that term, better throughput, better reach, all these neat things going on. So I came with the idea to put together a panel to kind of talk about some of those things, and this is that panel. And I'll introduce our speakers here briefly. If you want to read their bios, please feel free to do so. They're on the web. I am not going to regurgitate them for you. To my right, your left, is Drew Perkins, who from Infinera. He's the CTO there. Prior to that, Lightera, Force Systems. Got that right? Mm-hmm. Yeah. To my left and your right is Gary Nickel from Cisco. He's an engineer in their optical unit out of Ottawa, Canada. Not a marketing guy, so we won't have any of those here. To his left and further to your right is Ross Saunders from Stratolite, who has been involved in optical transmission systems since 1992. Did I get that right? And I think you guys are going to like this panel. There's some good stuff going to be talked about. I'm going to ask that you save your questions till the end. I do not want to see us get rat-holed between presentations and burn 20 minutes and then shortchange some of the other speakers. So if you all would be kind enough to do that, that would be awesome. And with that, we'll let Drew go first. Drew, you're on deck.
All right. All right, good morning, everybody. Thank you, Ted. I've got more slides here than I should, so I'm going to be going pretty quick through them here. Just a bit more on my background. I've been involved in the internet since the very early 80s. Actually, was one of the first people, the very first IETF, actually. And I've have a long background in internet as well as optical technology. Spent most of my life in sort of layer 3, 2, and 1, and on down. So this is my perspective on what's going on here, the next generation of optical transport and how it relates to IP. So this is just an agenda slide. We're going to talk a bit about Ethernet and how that relates to IP and optical transport. What we call super lambda services, bonding multiple channels together, 10 gig E, 100 gig E, and where we think it needs to be going as quickly as possible, terabit Ethernet. We talk a little bit about some work we're doing on reconfigurable IP router bypass. Mention a thing or two about modulation approaches, and then talk a little bit about photonic integration. And unfortunately, I'm not going to be able to cover any of these things in depth at all due to the brevity of time here, but ask questions later, please. So we've been doing an interesting study at Infinera. We've been basically modeling an IP network, a nationwide continental U.S. IP network from sort of top down, starting with, there's this much population in these areas of the country. And you have these pieces of equipment to build from, go to it, how would you do that? And we're developing an analysis system that does that. And so one of the first things, and I'll talk about a few things that we're finding as we do this, obviously it's kind of a no-brainer. Obviously 10 gigabit Ethernet wins on routers shipping today anyway. 10 gig E is much more cost effective than 10 gig PAWS or 40 gig PAWS. If you plot these curves out, basically the curves I'm showing at the bottom here, what we do is we're scaling an IP network from a range of 1 to 256 times as large. Somewhere towards the left side there, well, maybe a third in is at sort of a terabit level where a number of big carriers sit today, and going out probably another 5, 10 years as a scale their capacity. And no matter how far out you get, 40 gig PAWS sort of never catches up. I'll say more about that. So Ethernet, the future of optical transport really appears to be Ethernet based. It's by far the most cost-effective thing. It's kind of a no-brainer, mother hen apple pie, I'm sure. Just sort of definition of what we think. Oops, there we go. IP links, years ago, more than a decade ago, I guess, used to be what we call sub-lambda. That means you had a lambda, a wavelength, running across your transport network, and then you carved it up into TDM time slots using SONET SDH, and IP used a T1, then a DS3, then a OCE3, OC12. Finally, in towards the late 90s, IP caught up to SONET SDH, to optical transport, started using a whole wavelength at a time. You had the WDM systems, optical transport systems, emerge. And first we started using 2.5 gig wavelengths, then we stepped up to 10. Then, earlier this decade, we started to need more than a wavelength. And you started having to bond circuits together between adjacent core nodes in your IP network. We call that super lambda. We're using multiple lambdas to aggregate a link, to get a composite link, a link aggregation group, whatever you call it. There's a bunch of terms for it. Basically, inverse multiplexing of your IP packets over a number of different lambdas to get enough throughput, enough capacity for your IP to meet your IP service needs. All right. So if you sort of look at where traffic's going and has been going, a couple years ago already, we were using N by 10 gig, where N was as much as 8 links, 2 years ago or so. And this curve just sort of plots out a couple different growth rates: 75%, 100%, 125%. Probably should have maybe had 50% there, but even at the 75% growth rate, which maybe is close to where a lot of people are growing, you get out to, by 2010, you're looking at 1.3 terabits per second. Is the demand, the need that you have to scale your each link between core IP router nodes. So obviously there is nothing on the drawing board right now in the standards groups as far as terabit links, terabit Ethernet in particular, although it's been discussed a bit in the IEEE, and IEEE right now is working on 100 gig E. But so right now you got a bunch of carriers that are looking at putting in 40 gig links to upgrade from their 10 gig links, which are largely going to 10 gig E at the same time in some carriers. As I said before, the 40 gig really isn't cost effective, but you are getting a 4x jump in bandwidth perhaps. So at the IEEE, in the discussions of 100 gig E that have been going on, a number of carriers have come in and said, you know what, this 100 gig E is just not enough. It's what I need today. By 2010, I need terabit Ethernet. I need a whole lot more than that. Level 3's put out projections that are going to be running 150 by 10 gig between core nodes in 2010. And other carriers have made similar statements. So clearly, we need to be able to keep scaling the links between core nodes to pretty dramatic levels of capacity. And no matter what transport technology you're looking at, whether it's 10 gig, 40 gig, the 100 gig, a number of people are talking about 100 gig on a wavelength, you're still, in any case, even at 100 gig level, going to be putting multiple, having to bond together multiple wavelengths together. We're living in a super lambda world, and we're going to continue living there from here on out. All links are going to end up being super lambda here, between, at least within the core of your network, and even getting into the across backhaul links to tier 2, tier 3 links. There's no getting around that. So as I said, we're doing this study trying to look at the economics of building an IP network, a combined IP plus transport network, the whole shooting match basically. And this picture is just, this slide is just showing here, a network without router bypass, i.e. each core router is connected to its topologically adjacent neighbor, okay? Sort of the conventional way to build a network. People have been doing some amount of bypass, for many years, but mostly to a limited degree. This slide is just showing no degree at all, just pure no router bypass. That's sort of the baseline. All right. And as you do that, of course, what you have is you have IP packets. The core routers are serving a lot of transit capacity, right? The routers in the middle, a lot of their switching capacity is just going in, going out, again, from east to west, west to east, whatever, without being dropped at that local site or shifted, switched to a tier 2 node. There's just going from one tier 1 link to another tier 1 link. So you're spending, your routers, of course, are the most expensive part of your network. Routers today are far more expensive than transport equipment. You pay, almost an order of magnitude, maybe at least half an order of magnitude more per bit per second for an IP router blade interface than you do for transport. So if you're spending most of your router on switching capacity in and out, 75% or 90% of your capacity is just going in one high-speed interface to and out another one from one tier 1 node to another, you're spending an awful lot on using your router as a regenerator, basically. So it becomes increasingly inefficient. So what happens when you start adding router bypass to the picture, right? What I mean by that is let's start building a mesh at the layer 3 IP layer across the transport layer. So people, of course, have been doing this to a limited degree in the past. Most large networks do this, from DC to LA, New York to San Francisco, those types of links, but it's been very limited because it has limited cost effectiveness. There's a few places that there's very high demands going between, but not all that many. So we've been studying this and seeing, okay, well, if that's true, how does that scale as the network scales? As we get out to 2010 and beyond and we start getting to terabit links, what opportunities start presenting themselves to putting in IP router bypass links to shunt traffic directly across transport nodes and bypass intermediate IP routers, and what kind of cost savings does that get you? All right. So here you see a picture, a graph here, and these are somewhat preliminary numbers, but they're pretty much on target. What we see is that the ability to add in IP router bypass links increases over time as you scale your network higher and higher and higher. So what you see on the left, for instance, the very top graph, each of these lines is an amount of savings. It looks like my units got cut off on the left side. I'm sorry, but this is sort of 100% is what the network costs with no router bypass at all, and then as you go down to 60% or whatever, it's what your network would cost as you add router bypass links. Okay, and then each line is as you add scale to your network, which is basically equates to as if your network were doubling every year, for instance, then 5 years is 2 to the 5th, 64, 32 times, etc. And then the number there, the scale of the network is plotted. So what you see is that, and the other thing to say about this graph is, we stop the plot at the point where if you add another router bypass link to your network, it's going to get more expensive, not less. And what's happening there is if the network that we're modeling here happens to have 18 core nodes, so there's 18 times 17 possible bypass links between core nodes. And so out of that 306, how far do you get before it starts becoming more expensive? And what you see is at low scales, it only makes sense to add a couple, which is sort of where most networks have come from. Beyond just a few links, maybe 5, the network is going to get more expensive. And what's happening is that the demands between, if you look at the matrix of demands between all the core nodes, some are going to be, the very high ones are going to be more than a lambda, others are going to be less than a lambda. And if you're buying, if you need less than a lambda, but you're buying IP router interfaces on both ends to support that demand, you're going underutilized and it's becoming very inefficient. So the number of times you can do that, of course, grows as you scale the network. So even if the transport network were free, it doesn't make sense to put all of your traffic in a full mesh configuration because you're underutilizing the router interfaces to a great degree. And this is sort of a fallacy. There's a lot of people have an all optical switching model where they assume that eventually the network's going to scale to being all optical switches in the middle and just IP routers at the edge is sort of one of the visions of the industry. That vision, turns out, doesn't make any sense at all. You're always going to need IP routers to aggregate traffic because that full matrix, if you plot it out, there's many links. It's a sparse matrix where it makes sense to actually put these things. All right, so if that's true at 10 gig, what happens at 40 gig? Well, the answer is that 40 gig already starts out less cost effective than 10 gig E if you're using that. 40 gig, now your lambda is running faster, which means that the demand necessary to make that bypass link make sense needs to be even greater, which basically means your whole curve shifts. shifts right or left, depending on your perspective. So it makes less and less sense. And what's going to happen is we get 100 gig, it makes less and less sense. So there's basically a tension between the demand, the capacity of a single wavelength, 10 gig, 40 gig, 100 gig, versus the scale versus putting in these router bypass links to where you get the most cost-effective bandwidth. Right? Now also, as you start putting in IP router bypass links, you also create a need for being able to reconfigure your optical transport network because as traffic shifts, as new sources pop up, new popular websites, sporting events, whatever, as IP peering, BGP adjacencies come and go, whatever, traffic shifts pretty dramatically sometimes, you want to be able to reconfigure your transport network on the fly to do that. So that's something I'd like to do. So the vision in the industry right now is all optical ROADMs to be able to do that, be able to switch all optically. As I said, that will make sense for some amount of these bypass links, but given the limited use of these bypass links, depending on scale, it makes more or less sense. And of course, ROADMs, all optical networks have a bunch of problems or issues because there's no OEO going on. So there's no wavelength interchange, there's no regeneration, there's no performance management, OMP, et cetera. Excuse me. And also there's wavelength contention and blocking because there's no wavelength interchange going on, which makes routing through that network be even more expensive. And what you see is that what our studies are showing is that there's a 30 to 40% incremental cost on the OEO side. Now, if you're using your routers as your OEO to switch wavelengths, you're using the most expensive device in your network to do a pretty simple transit function. So also your service becomes limited by the wavelength path because of reach, number of ROADMs you pass through. Every time you pass through ROADM, you decrease your reach, et cetera. Right? We believe that the right answer is what we call digital ROADMs, which are every node is a capable full OEO and therefore full wavelength interchange, full statistics, et cetera. But through photonic integration technology, it becomes very inexpensive to do that. You get digital protection in the optical layer as possible. It's another interesting thing that we're seeing that historically it's been the case that it's made no sense to do protection in the transport layer. Once we went to the lambda level beyond SONET, when we had SONET, we did protection in the SONET layer. When we went to individual lambdas, all protection is done at layer 3. That's the most cost-effective thing. It's non-intuitive, but what our studies are showing is as the network scales to much higher, in a few years from now, basically, it actually starts to make more sense to do some amount of your protection in the optical layer again, in the transport layer. And we'll be back hopefully to talk about that more as we study that a little further. So anyway, if you can do things digitally because you've made OEO less expensive, yet you give yourself a degree of freedom that unconstrains you for digital add and drop. Right. So the question now is sort of how are we going to keep scaling capacity in the future? We're going from 10 to 40, 100. Where are things going? There's lots of different ways to scale capacity in your network. There's the simple tried and true approach of space division multiplexing. Give me another fiber, give me another circuit, give me whatever, parallel optics, et cetera. There's time division multiplexing, just pure TDM. That's sort of been tried to go from 10. At 10, we kind of hit a roadblock there. It was tried at 40. The first generation of 40 gig stuff did NRZ. It turned out that ran into so many problems because of dispersion, polarization, mode dispersion, chromatic dispersion, all kinds of things, nonlinearities. People are now stepping back and using fancier modulation approaches. And it looks like we're starting down a road where the first thing was sort of duobinary, and there's a whole bunch of different terms. I can throw acronyms all day at you, but at the end of the day, things may very well end up much like in DSL or cable modems or wireless, where you're going to big constellations of QAM. And I'll be surprised if we aren't talking QAM 1024 several years from now, but we'll see. And of course, there's the also tried and true wavelength division multiplexing. So all these things are really equivalent. You can get additional capacity by doing any of these things. The question really is one of economics. And so just looking at history as a guide here, what have we seen with 40 gig? It was darn expensive. We didn't get a 4 times bandwidth increase for 4 times the cost. It turned out much greater than 4 times the cost. Right? Wasn't 2.5 times as we wanted. Right? A lot of people in the transport industry are now talking about 100 gig per lambda. There's lots of different approaches being thrown out. Sort of the biggest one, most popular one being thrown out is dual polarization QPSK, quadrature phase shift keying approach. Basically, you're taking your 100 gigabits, you're really dividing down into two 50 gig channels, sending each one over different polarizations. So you're doing polarization division multiplexing across your fiber as well as wavelength division multiplexing. Each of those takes more components. And then within each polarization, you are doing a QAM4 basically, trying to get 2 bits for every symbol across your network. You're basically building a big modem. And what we're seeing so far is that even at the 40 gig level, the best chip available now that's been published is burning 21 watts to do that kind of modulation at 40 gig. Nobody knows yet what it's going to take at 100 gig, but the answer is undoubtedly much more than that. So it becomes very power hungry, which equates to almost directly to cost, because power dissipation is the most costly thing to do. But also, it's clear that you require significant integration to do this approach as well. What will it cost? I saw it just last week at a conference, one vendor was suggesting that it's going to be about 2.5 times the cost of 40 gig. So 40 gig and 100 gig will be at parity on a cost per bit basis. Well, 40 gig is much more expensive than 10 gig. We think that people are just going to stay at 10 gig for quite some time, at least for a lot of networks. So 10 gig, of course, Infinera has been shipping 10 channels of 10 gig integrated on a single chip, photonic integrated circuit as it's called, since 2004. Right? And we predict the cost of that's going to keep going down. So the interesting thing about PICs is 10 by 10 isn't the limit. We've published papers on 1.6 terabit PICs that run 40 channels of 40 gig. There's a lot of room for growth there. And not only are you going to need to increase the line capacity, a single line card, you want to get that scaling from 10 to 40 to 100, where we are today, to 400 or 1,000 terabit level. Also want to scale your line bandwidth. Infinera's shown some approaches published in papers now on PIC-based, what they call SOAs, semiconductor optical amplifiers, that can give you a much greater bandwidth across your fiber than today's erbium-doped fiber amplifiers. So there's a whole lot of approaches to go from 1.6 terabits, for instance, to tens of terabits. I just read a paper the other day that showed how to get to 150 terabits across a single fiber. So there's lots of ways to get there. In summary, I'm just say that it's pretty clear that Ethernet is going to continue to is already and going to continue ruling the day economically. We believe, at least as the interface. Super Lambda is here to stay. It's going to remain the norm and become more popular. But it's very important to integrate that. And optical transport has to become much more flexible to enable much more IP router bypass, because that's the least expensive way to get there. And multi-terabit line systems are going to be necessary. Terabit line cards required. So all that's going to take massive integration, whether you're doing pure WDM or TDM or fancy QAM modulation. Integration's necessary and all that stuff. Thanks.
I don't know where. Val, where'd you put these?
Pull that one up.
It's not around.
Good morning. Thanks, Ted, for inviting us to this conference. I must admit I didn't understand too much of the talks that have been going on today, so it's time to get my own back here with some optical stuff, and I will be throwing a few acronyms out here, so apologies up front for that. What we're going to talk about now is it's really the alternate religion to what Drew's been talking about there. Drew's really talking about basically building more lanes on the highway and keep sticking with the same speed, whereas our religion is much more on trying to increase the speed on each lane. So that's increasing the capacity on each wavelength. One of the critical things is trying to see if we can engineer 100 gigabit modems so that they can plug into existing systems, which basically means in the long haul network, existing 10 gigabit systems. So introduction, 40 gig market is really just beginning to take off. I agree with what Drew said, the price point is still more than 4x 10 gig at this point in time. It's on a steep cost reduction curve as the volume picks up, but it is more expensive. It is being deployed by some very large carriers, and that's really driven by the increase in capacity. You can't just look, if you just look at the cost of the transponder versus 410 gig, the economics don't price in. You have to look at a total cost of ownership where the IP traffic is growing so fast that carriers don't necessarily want to be burning through multiple DWDM overbuilds, which cost money to buy those new WDM systems, to install them, etc. So that's where we are at the moment. It's just in its infancy, but growing pretty fast. Really driven by a lot by converged IP networks, video distribution, peer-to-peer video, video on demand, all that stuff is really scaling it up. And pretty much most of the estimates out there are the core network will more or less double every couple of years. So that's very high growth curve there. Optical transport spectral efficiency. So this is the capacity that you can get per fiber, and the port speed coming off the IP routers, Ethernet switches, etc. has to keep pace with that growth. And this is the growth curve. I mean, we're back again to 2000. We can pull out the same curve again. Hopefully, it doesn't go the same way as it went in 2002, 2003. But it's all been driven by video and lots of good growth there. 100 gig requirements. There's a whole bunch of detailed requirements here in terms of really just making it work on the existing infrastructure. So, the current standard in terms of long-haul network is 50 gigahertz WDM channel spacing. To keep most carriers happy, at least in the US, they want a 1500 kilometer or greater reach. There may be metro regional opportunities in other national areas, Asia and Europe, where the reach can be a bit less. Really, all of these things at the end of the day come down to you got to make it work with what's installed in the field. So you can just plug this new technology straight into existing systems. That's really what's helped with get the 40 gig market started. Is the fact that 40 gig was engineered so that you can plug it into those existing systems, which means more advanced modulation formats, higher spectral efficiency. But that really enabled the market to get going. If you require a carrier to deploy a whole new WDM line system, then it becomes a tougher sell, because now there's a big cost associated with deploying a new system, certifying a new system, training the engineers to work on a new system. So that mantra, we're trying to keep that in mind as we go towards engineering 100 gigabit systems. Some of the technology considerations, you've always got to trade off complexity for performance, and as you go to more complex solutions, it does drive up the cost as well. So you have to keep that discipline there. Many of the schemes also trade off spectral efficiency for reach. So as you go to higher levels of coding, then usually that involves a reduction in the signal-to-noise ratio, and hence a reduction in the reach. Another part is that you've got to use practical electronics. So at the moment, even at 40 gigabit, we are using leading-edge electronics processing speed. So it's the same as we move to 100 gigabit. You've got to be able to use existing production-qualified electronics transistor technology. Electrical signal processing in general is lower cost than optical. So once you get the volume up there, the cost of the chips is certainly lower cost than the optical compensators. So that's again something that we've got to keep in mind as we engineer these solutions. And also you can gain a lot of insight from other industries. So a lot of other industries have had to fight the spectral efficiency battles before we have in optical. So you can look at wireless GSM, use some advanced modulation formats, minimum shift keying, HDTV, using trellis-coded modulation, some advanced FEC, satellite using quadrature phase shift keying, quadrature amplitude modulation. So again, high spectral efficiency there. WiMAX, using orthogonal frequency division multiplex, another technique with good spectral efficiency. So you can look at all these different industries and say, okay, how can that help us out to get higher spectral efficiency at 100 gigabits? Again, bearing in mind, you've got to use practical electronic speed, because optical's bandwidth, port speed is obviously much higher. Also, the use of DSP is immature in optical communications, so we can predict that's going to become a more important component of the overall design as time moves on. The other thing is fiber nonlinearity. So there is a nonlinear effect in the fiber that you have to watch the amount of power that you can launch. This applies to today's systems, but when you go to higher line rates, more advanced modulation formats, that becomes an even bigger constraint. So it's not like wireless, where in general you can keep jacking up the launch power there. We have to watch that with the optical domain. So apologies, this is acronym soup here I've thrown at you, but basically there's a map in all different kinds of modulation formats, and you can look at the pros and cons. Here we're looking at spectral efficiency versus optical signal-to-noise ratio. So really, to be in the zone where we have something interesting, we want to really be in this green quadrant. Ideally, we want to have a spectral efficiency of 2 bits per second per hertz. That enables you to deploy 100 gigabits on 50 gigahertz channel spacing. And in terms of optical signal-to-noise ratio, if you get in this regime of 12, 13, 14 dB, now we're in the regime where we can do 1500 kilometers type reach. So that's the kind of design target area. If you look at some of the other options, like OOK is basically on-off keying, which is pretty much what everybody's used for 10 gigabit. That doesn't have the spectral efficiency or the reach. So that is the simplest format, but it just doesn't work for 100 gig. Some other formats, optical dual binary, you've got better spectral efficiency. It would work on a 100 gig grid, but doesn't have the OSNR sensitivity. Wouldn't have good enough reach. You've got some other formats, quadrature phase shift keying, differential quadrature phase shift keying. These ones, again, 1 bit per second per hertz. They're a bit better OSNR, a bit better reach, but you can't get the spectral efficiency. Really, then you've got 16-level QAM, which has got multiple levels between it. It has very good spectral efficiency, but you lose some in terms of reach, so you wouldn't be able to hit the 1,000 kilometer plus type reach. Polarization mux, that's what the PM stands for there, QPSK, PM DQPSK. Now we can get down to a 25 gigabaud rate, so you're coding 4 bits per symbol now. You've got the spectral efficiency you need. Reach is getting there, it's still a challenge. Really, to improve the reach, we really need to go to next generation, either trellis-coded modulation or soft decision forward error correction, which kind of gets you closer to the theoretical limit, the Shannon's limit, as we call it, on signal-to-noise ratio performance. So, there's a lot of advanced stuff required to get there. If you look at implementation complexity, which does translate through into cost there, you've got a trade-off between the electronic complexity and the photonic complexity. So, of course, the formats that are easier to implement have lower complexity, but they don't have the reach or the spectral efficiency. So, looking at these advanced modulation formats such as PM-DQ-PSK or PM-QPSK, that's increased the photonic complexity quite a bit, especially the PM-QPSK, which requires a coherent detection, which is really something new in the optical domain. It's used all the time in other industries, but to do it optically is certainly more challenging there. When you look at these PM-DQ-PSK, PM-QPSK, the electronics is not as bad because you're down at a 25 gigabaud rate, which means you can use lower speed electronics. So that's that is doable from that side. This just shows you the kind of transmitter receive block diagram for one candidate format here, 100 gigabit polarization muxed QPSK. It's quite complex. I mean, if you compare this to an on-off keying block diagram, it's there's a lot more boxes on here. That does translate through into cost there. In this case, we have a couple of modulators here. You're modulating 2 different polarization tributaries. You've got 4 driver amplifiers on the transmit side, so there's a bit more complexity there. The good thing is, to make it practical, is you're operating at this 25 gigabaud rate. So, effectively, the driver amplifiers are lower bandwidth than we use today at 40 gigabits. Because 40 gigabit systems that are deployed, they're operating at 1 bit per symbol, which is with FEC is a 43 gigabaud rate. So some of the electronics here is actually lower speed. On the receive side, you've got more complexity. You've got a coherent detector, so that needs a local oscillator, which is basically a tunable laser. and you need a phase and polarization diverse receiver. And to do the phase estimation and do the coherent detection, synchronous coherent detection, you need an analog digital converter and digital signal processing there. That is a new chip which is pushing the limits in terms of the electronic speed. Some of the enabling technologies that help us to get there is you kind of approach this from there's two main tools that can help you get there. One is use modulation scheme to try and make your higher speed wavelengths operate over current systems, and the other side is to use dynamic compensators, and you can do that optically and electrically. So some of the key technologies today is an optical tunable dispersion compensator, which is a device called a fiber Bragg grating, which basically if you have large amounts of chromatic dispersion in the link, you can basically bring the pulse shape back together again by this chirped grating, which is it basically just it reflects different wavelengths of light at a different point down the grating structure. So this is critical. It's helped us at 40 gig and is likely to help us at 100 gig as well. Also, we have a polarization mode dispersion compensator. PMD is they're called single mode fibers, but they really have two polarization modes. And in older fibers, you can have dispersion between the two of those. So you have to be able to combat that to make 40 gig and 100 gig work. So that's another critical technology. Moving on to some of the coherent detection schemes, when you have an A to D converter then into a digital signal processing chip, when coherent detection, one of the advantages is that you pass the optical phase into the electrical domain. That doesn't happen for the direct detection mechanisms. So now when you pass that phase into the electronic domain, now you can digitize it, quantize it, and you can use digital filters, finite impulse response filters, to combat some of the nasty optical effects such as PMD, chromatic dispersion, cascaded filter tolerance. So this is something that is going to help in the future. We'll go through this in detail, but basically at the moment we're already using the state-of-the-art qualified electronic processes, and to do some of this advanced stuff, especially the fast analog digital converter, we really need to go to the next generation CMOS, 45 nanometer CMOS, or next generation silicon germanium by CMOS, which is around the 300 gigahertz FT, which is the transistor process. Roughly, you need a rule of thumb where you need 5 times the transistor speed, 5 times the data rate to be able to make it work. So when you go down to the 4x25 gigabaud, for the analog digital converter has to do 2 samples per baud, which means you're up to the 60 gigasample per second type speed to make that work at 100 gigabits. So that really needs a fast next-gen electronics process. So we are at the bleeding edge of electronic speed. I won't go through all the detail here. It's on the web there if you want to look through it. But certainly when you compare the different options here, to a large extent you do get what you pay for. I mean, if you want to make it work over a 50 gig grid, if you want to be able to hit the 1500 kilometer reach plus, you are looking at a PMD-QPSK or a PMQ-PSK type modulation format, and there is a cost premium to pay for that. So, there's you got to bear that in mind. Really, if you look at 100 gig, it's going to be similar to where 40 gig is at the moment, where you have to look at the total cost of ownership, where you look at, okay, am I going to be scaling my IP traffic so fast that I really want to be able to deploy 100 gigabit channels on a 50 gigahertz grid, which effectively gives you an 8 terabit capacity per fiber. If you have low capacity growth, maybe it's not the right option for you. You're maybe better going with some of the options that Drew talked about. But certainly, if you follow this growth curve at 2x per year, in reality, for 100 gigabit to be mature, for all the bugs to be ironed out, to be really field deployable in a carrier network, it's probably 3 years out. So, 3 to 4 years out. So if you look at the growth curve of the capacity by then at least in those highest capacity networks, we feel there's still going to be a need for it. Just to summarize, the traffic growth has been fueled by video, IP-rich media. Got the hockey stick growth curve there. And again, we've got a plan on this network traffic growth to double every 2 years or so, at least until 2011. Who knows beyond that? Deploying 100 gigabit wavelengths using 10 gig rules, it is feasible. It does require this very high spectral efficiency. We do have to go to more exotic modulation formats to make it work. But it is possible through these advanced schemes where we're coding multiple bits per symbol. So it is taking the modulation scheme to the next level there. Reach is still a challenge. We really need to get up to that 1500 kilometer type reach. Really need coherent detection and/or next generation forward error correction that gets us close to Shannon's limit, to the theoretical limit there. The optics is fairly easy. It's fairly straightforward at 25 gigabaud. You're not pushing the boundary in terms of modulator bandwidth or photodiode bandwidth. It's really still the challenge is on the electronics side in terms of the making it work. I would say the optics is still a challenge that you do need some level of photonic integration to be able to get the cost down a bit, but the bandwidth is not going to be an issue there. One of the critical developments that we need is an extremely fast analog digital converter, digital signal processing chip, and that will be one of the key areas of development. Thank you.
All right, next and last is Gary, and then we'll have some questions. I would like to reserve 5 minutes of question and answer for the panelists amongst themselves first, and the old NANOG theme of let's throw tomatoes at each other.
You didn't tell me that when I signed up for this. Hi, so my name is Gary Nichol. Work in the co-writing group out of the Ottawa office in Canada. I guess my talk basically leads on from the talk from Drew and Ross, talking about really the impact of all this on routers. Now, I've been in Cisco for about 10 years now, working on the evolution of primarily on the optical interface in the routers, and I've seen the optical interface speeds increase dramatically over that time from maybe OC 312 when I started to 10 and just now 40 gig recently. But if I look at that primarily to date, those optical interfaces have been very simple in a couple of respects. That they've primarily been focused on just doing very short reach interfaces, predominantly 2 kilometers. That's predominantly because you want to connect one box to another box within the POP, or maybe you want to connect one router switch to a transport box, which then basically is responsible for transporting that thousands of kilometers across the country. And again, in terms of the optical technology, as Ross has mentioned, to date up to like 10 gig anyway, it's been very, very simple, what's called on-off keying. Basically, you turn the light on, you turn the light off. The light on is a 1, the light off is a 0. And it's been very simple. Now, as we're looking to go to higher bandwidth connections at 40 and 100 gig, as again, I think Ross alluded to, we're going to be looking at a lot more complicated modulation schemes. And then again, as Drew alluded to try and keep the cost under control, what we think is that a lot of those modulation schemes will actually sort of migrate and be implemented on the router directly, so the router can basically derive those long haul distances directly, and you don't need additional sort of costly high-speed short reach interfaces to connect to a transport box. I guess I should put this on to slideshow. Yeah. Do that. There we go. Okay, so this is my version, not quite of the growth, not quite as visually appealing as Ross's hockey stick, but it's basically telling you the same message. A couple of interesting bites in this, that people are projecting the traffic to grow to about 11 exabytes per month in like 2009, 2010. Now, until I put this presentation together and talked to our marketing people, I'd never heard of an exabyte, but apparently 1 exabyte is 5 times the world's printed matter, and 5 exabytes is all the words ever spoken. So that really sort of puts the sort of growth in context. And then this growth has been alluded to before, has primarily been driven by, or exclusively driven by data. Primarily driven and by sort of applications, both legacy and new applications. As we know, like a lot of the legacy applications are actually migrating to an IP infrastructure. Even things like standard sort of broadcast sort of video for cable is moving from what in the past was probably a proprietary analog distribution technology run basically on an IP backbone directly to your set-top box. Voice obviously moving to voice over IP. Then there's a whole range of obviously new applications exclusive to IP that are obviously driving up the bandwidth. And another statistic that I heard is that people project, if you look at the household bandwidth demands for like 2010 due to all these new services and applications listed above, that 20 such homes in 2010 will generate more traffic than traverse the entire internet in 1995. Now, Ted did mention that should be careful saying that up here because somebody might refute that, so that's certainly a data point that I've heard and seen presented a few times. But point being, anyway, there's a lot of bandwidth with growth there. So again, given all this, where does this take us to? Obviously, we're going to need higher bandwidths to address this growth, and I think all of us in the panel are essentially saying the same thing there. 10 gig networks today are beginning to feel the strain. And if you look at a lot of the core networks today, people are actually starting to aggregate sort of multiple 10 gig streams together to address the bandwidth demand between some of these core POPs. If you look at how you address that higher bandwidth demand, there's a number of ways you could do it. One way you could just use L2, L3 link aggregation, aggregate multiple smaller pipes together on the router switch. But really you can't rely on that. That's not a scalable solution sort of going forward. There's obviously a number of issues with the efficiency of that, as we know, and probably a lot of people in this room will know that on the efficiencies of some of the algorithms, the hash algorithms used to sort of aggregate traffic at layer 2, layer 3. They don't scale very well, and the sort of throughput of those is not deterministic. It very much depends on the statistics of the bandwidth. And really what that comes out to, if you look at doing anything at layer 2, layer 3, 4 by 10 gig does not equal sort of 40 gig. So again, we have to be careful when we're doing these comparisons of like 4 by 10 versus 40, because it may not be just a straight comparison if you're trying to do it at layer 2, layer 3. So the other approach, and again I guess is what Drew was alluding to in his talk, is okay, we'll have a nice big fat pipe at the off the router or the switch, and then but we'll still do some aggregation at layer 1, so run that over sort of multiple lower capacity wavelengths, say 10 gig, and address a lot of those sort of link or lag issues. So that, again, has probably got more mileage, but fundamentally at the end of the day, that approach does not scale as well, because ultimately your DWDM systems, the ports are not unlimited. Okay, maybe you've got a 40 or like a 40 or 80 channel DWDM system in the ground today, and as Ross mentioned, like typically customers want to use up those ports as efficiently and as slowly as possible, because once you've used them all up, it's a fairly major retrofit to install a whole new sort of DWDM system sort of going forward. And so what it really leads to is that really you want to increase wavelength capacity like as soon as it's viable, and that really means moving to higher data rates per lambda. So going to 40 gig, which people are starting to deploy now, and obviously a 100 gig looking a little bit further out. And again, as Ross mentioned, that these must operate over existing infrastructure. We can't have to just install a whole brand new transport infrastructure to be able to carry these 40 and 100 gig waves. You want to be able to run it over the systems that were installed, like probably during the bubble times, which were originally installed to carry 10 gig per wave. So you want to run 40, 100 gig of those, and ideally you want to run it with the same performance to 10 gig. And by that I basically mean in terms of the distance you can go. And I think as Ross alluded to, typically people are looking around sort of 1,500 kilometers, and that's sort of the target we're trying to get to with some of these new high-speed links. And again, I won't go through these, but to do that, once you're talking 40 and 100 gig, does require us to move to some more advanced modulation schemes, and basically the whole alphabet soup that Ross went through. that I won't go into in too much more detail in this talk. So in addition, if you look at bandwidth's growing, it's been essentially driven by IP. If you look at what that means to the network, it does provide the opportunity to significantly simplify the network and resolve down primarily to two layers: a service layer that's predominantly converging on IP, and a transport layer that's really converging onto DWDM as providing the connection, or the big fat pipes between those service layer router switcher nodes. And again, it's interesting to step back and look at that as well, because I've been in the industry for like 25 years. First half of that was working in transport. Transport started off really as a single service transport. It was providing transport for, at the time, voice. And then over time, it really migrated into more of a sort of, the transport network multiplied into more of a multi-service entity, where it had to provide transport not just for voice, but obviously for data in its various forms like ATM and frame relay and IP and lease lines and sort of stuff. So you end up with sort of fairly complex transport network that had a whole aggregation layer built in to handle these multi-services. And what I see going forward is that we'll actually migrating back more to a single service transport network, where again the transport network is really just providing transport for IP between these switches and routers. And I think, again, if you look at that a little bit further out, then it makes a lot of sense to actually integrate a lot of that DW, or closely couple the two layers and integrate a lot of that DW technology directly onto the routers, we'll see in some later slides. So that's, I guess, what we call IP over WDM. Again, just integrating the DWDM directly on the router. The picture in the top right is really the present mode of operation, where the bit on the right is the transport layer. And what that's trying to show today is that the transport layer is sort of multi-service. You've got some transponders connected to routers, you've got some other transponders at the bottom there connected to transport other services. So the transport layer is predominantly multi-service, and because of that, you've typically got these transponders there, because the transponders are really a multi-service that allow you to connect the transport layer to all the different service types that it's transporting. And it sort of makes sense to do that, and that provides a nice clean demarc between the transport layer and the multi-different service nodes it's providing transport for. But again, as we can see in that top right-hand picture, it does require some more functionality on the transport gear. It does require, what I'm trying to show there, like if you look from the router, short reach interfaces, which are the little blue boxes there, connected to the transponder, which then converts it into a sort of colored lambda for connection across the transport network. Now, if we move to the bottom picture, which we're calling IP over WDM, this is sort of where we're looking. Okay, so the transport's moving more to sort of single service, and it's only providing transport for IP. In which case, then it would seem to make then a lot of those transponders that were there to provide that multi-service aspect and to provide that demarc point, the value of that somewhat becomes less and less, and it allows you to basically then move the transport into the router itself, what we're trying to show in the bottom. So we basically have the colored optics directly off the router, and that really is really sort of reducing all of the costs, because we've taken out a lot of the short reach interfaces between the router and the transponder, a lot of the actual optical interconnects between the router and transponder, and limited the transponders themselves, which basically eliminates a lot of the common equipment that it goes around with actually supporting these transponders. So basically overall allows you to move to a much simpler and we believe lower cost network. This is the one marketing slide that I threw up here, so I won't spend much time on it. It just, other than say, like, again, this is not just chartware. We have a sort of 10 and 40 gig DWDM interfaces on the router today that are actually deployed sort of in the field and sort of carrying sort of live traffic. And the one point there, we've got 40 gig, I guess, deployed over links of up to 900 plus kilometers. So again, just looking a little bit more about 40 gig and 100 gig technology in detail. So 40 gig, so as we mentioned, routers prefer a single 40 gig pipe for the lag and load balancing limitations. Customers that we talk to prefer single 40 gig per second interfaces. And primarily that's because the deep-ground transport doesn't have limited ports. It's often viewed as a fixed and sunk asset. It's installed in the ground. It's got a certain number of ports. And people would rather turn up sort of one port for 40 gig rather than burn up sort of 4 ports. And obviously, to Drew's point, like, yeah, cost is important, and there certainly is a balance there. But what we're seeing is that people are prepared to pay a premium up front initially for that spectral efficiency. And good example of that, let's say we've got both 4x10 gig E actually, and 40 gig DWM interfaces off the router, but most of the interest and most of what we're selling is actually sort of the 40 gig card and not the 4x10 gig card, which somewhat surprised me because it is significantly cheaper and you can actually go a lot further today with it. But we're seeing that basically across most of the customers we're talking to. So looking forward in terms of the modulation technology, as Ross mentioned, that is advancing rapidly from like optical geobinary today to sort of DPSK to maybe looking a little bit further out some of the coherent technology that Ross was talking about. I think one of the advantages of the coherent technology is, as Ross, it actually allows you to do a lot of the processing electrically and not optically. So you basically do a sort of an A to D convert right at the front end of your receiver, and then you can actually compensate for a lot of these things like chromatic dispersion and PMD electrically, which again ultimately over time should be a much lower cost solution because, again, looking back in my time in the industry, typically doing things electrically is more cost effective than doing things optically. So we've already showed that 40 gig today can run over existing DWDM infrastructure. That's typically using optical geobinary. Does have some limited limitations in terms of sort of the performance and reach, but with some of these newer technologies that are coming on stream over the next few years, that we will be able to get 40 gig sort of meeting, or in some cases actually exceeding the 10 gig performance. And again, just from a router perspective, the key thing there is that all these advanced modulation schemes can be integrated and you can drive it directly off the router blade. So then just moving a little bit about 100 gig. 100 gig is real. Customers are requesting today. Both the ITU and the IEEE are already taking up the effort on the standard. A number of the people I've seen in this room are actually helping out with that in the IEEE. I think they've been working on it for about a year now. Key thing I guess here as well, like again, because this is a new standard, like we're not talking 100 gig tomorrow. For the actual IEEE to complete the standard, I think the schedule is sort of 2010. So again, when you're looking at a lot of this stuff and maybe comparing to 10 gig cost, you don't want to be doing it today. You want to be looking maybe 4 or 5 years out when this 100 gig technology will start to be deployed. So the other points beneath it are pretty much the same as before. Like at 100 gig, routers still prefer a single 100 gig interface. Customers who we're talking to still prefer to see a single 100 gig interface, basically 100 gig per lambda. That's been achieved at 40 gig. It's obviously more challenging at 100 gig, but again, as Ross mentioned, that basically we can leverage a lot of the work we started at 40 gig in these advanced modulation schemes to achieve sort of 100 gig per wavelength and with sort of equivalent performance to 10 gig. And again, at least from my perspective, what's important is that a lot of these things that Ross is talking about can be integrated directly onto the router as well. So just quickly to wrap up, IP traffic is obviously continuing to grow, as we've mentioned. What that means is we need fatter pipes, not more pipes. We need that both at the service level, like at the router, as we mentioned, due to the lag and load balancing limitations. I also believe that fundamentally we're going to need that at the transport layer as well, because transport systems do not have unlimited ports, so we have to look at continuing to increase the speed per wavelength. That does require advanced modulation formats. That the fatter pipes we're looking at, both 10 and 100 gig, do need ultimately to match the performance of the skinny pipes today. And again, that's probably going to be in performance both in terms of distance and ultimately in terms of cost as well. We see the network converting to 2 layers, service and transport, and then a closer coupling of those two layers, we believe is the next obvious step in network evolution. I think that's okay, and that's it. Thank you very much.
All right, I'll kind of wrap this up here for us guys up on the panel, then we're going to open up to you guys. Like I said, I want to give the panelists a few minutes to ask each other questions if they have questions, like we used to do in the old days at NANOG. And just to kind of reiterate what they say, I also agree, we're kind of moving into a binary world. It's ones and zeros, IP and transport, optical, and they're all going to be the same thing. And it's best for everyone to start paying attention and learn it. There are some people actually working on optical routers, as in like light. And it's not just science projects anymore in weird universities. There are little startup incubators looking at this stuff. So it's coming, for real. So with that, we'll open it up. Drew, Gary, Ross, do you have any questions for each other? Or are you guys going to be nice? Are you going to wait for the next IEEE meeting to eat each other alive when you're not in front of the audience? Or in the bar? All right. They don't have any questions for each other. All right, we'll open up to the audience. Anybody in the audience have questions for the panelists? Please come forward. Mr. Myers over at the left mic. It's on.
Okay. First off, nice. Maybe you can repeat my question. You guys talked a lot about physical layer stuff. It's an optical panel, I understand. What I'm curious to know is whether eventually we're going to hope that we can plug in 100 gig circuits or interfaces into routers, which sort of means that eventually we're going to need L3 engines that can do on 100 gig. We're going to need BOQ chips that can do 100 gig. We're going to need L2 framing and all of that stuff at 100 gig. What is your sense, this is sort of a generic question, what is your sense about where that technology is as compared to where sort of the PHY technology is today?
It's definitely a long pole in the tent. There's certainly a lot of people working on it. And there are no chips available today, as far as I know, and hopefully I know what's most of what's out there. But I think that's there are maybe 3 long poles, as I said, and that's definitely one of them.
Gary? Yeah. Give him a second. There you go.
Hello? Oh, there we are. Yeah, so I guess the short answer is yes. Where are they in terms of, I guess I'm an engineer, so I better be careful what I say here. Yeah, both, there's definitely, as Drew said, there's advances in terms of the engine technology. There's obviously advances in terms of the PHY. There's advances in terms of PHY just to do like the short reach interface, like how do we get a 100 gig short reach interface across the office, and then how do we get 100 gig across the country. So there's really those 3 aspects to it. I think there's active work going on in all three areas right now. As I mentioned before, like this has been worked on by the IEEE and the ITU. I think the schedule is to around 2010, I guess, for that to be sort of fully ratified, and I would expect all of those 3 components to be available in by that time frame. Maybe is the best way to put it.
The other component, or the other piece of that question I forgot to ask that I wanted to ask is, what kind of power envelope is 100 in your with optical is 100 gig, just a single port now, 100 gig line card going to look like?
Talking power dissipation or optical power on the fiber?
Power requirements and heat dissipation on the line card.
That was actually going to be my question to these guys, actually.
So I
What do you
think
guys?
I think the targeted goal is obviously to try and do 100 gig within the same power budget envelope as as we have today on the 40 gig per slot.
Yeah, exactly. It's got to hit the kind of 100 to 150 watt range. But one thing I didn't agree with Drew is that's not a major cost driver. It's more you've got to make sure it can plug into existing routers and existing WDM systems, and you've got to be able to cool it. I mean, those are the challenges. It's not that the power consumption per se is a big cost element.
Certainly a fascinating thing, I think, that's going to cause some thinking going on in the industry from my perspective is if you're just trying to come up, just do a short reach link within a POP or something between a router and a transport gear, for instance, multi-mode fiber ribbon technology is going to be far less expensive, far less power, and far sooner availability than anything over single mode, over a single mode anyway. I just I'm curious what's going to happen when people can buy multi-mode fiber ribbon interfaces a year earlier for a tenth the cost. We'll see.
Mind you, the same thing happened with 10 gigabit, right? And
Yeah.
the problem is none of the big carriers have that multi-mode ribbon fiber distributed through their distribution frames. So, you know, even though there's a big cost difference, I'd imagine it's still going to be an issue there that, you know, they want to go above the 300-meter reach, and, you know, they don't necessarily want to have to deploy new multi-mode fiber. You know, even though there's a 40 gig, there's obviously a big cost premium there as well. I mean, 40 gig short reach interface is a single, you know, it's a serial 40 gig interface. It's expensive, as Gary said. That's why there's value in integrating the WDM on the router there. So, yeah, if it's not going to happen there, I'd still be surprised if those carriers are going to go for the pain and investment of putting that multi-mode fiber ribbon cable distribution in there.
I think Gary can tell you about what happened to 10 gig though, and I think you have some experience on shipping multi-mode fiber ribbons at that level, right?
Yeah, again, as Ross alluded to, we actually came up with a scheme called OC192 VSR at 10 gig. We actually did run 10 gig at the 10 gig serial at the time. This was back in 1999. It was extremely expensive, and we came up with a scheme of running OC192 over sort of ribbon fiber. It was significantly cheaper, but again, it was not widely accepted by the industry for the reasons that Ross talked about. But it did have the advantage of driving down the cost of 10 gig serial, because it was a much lower cost solution that helped all the serial optical vendors sharpen their pencils, and really did have the benefit of helping drive down the cost of serial 10 gig quicker than it might have done if we hadn't come up with that solution.
On a realistically desirable deployment distance, 1,500 kilometers has been mentioned. If you apply all of the advanced technologies that have been mentioned, what is the theoretical limit?
Theoretical limit of what?
I mean, if you get PMQPSK next generation FEC, you can do more than 2,000 kilometers.
What is the theoretical limit for the amount of data that can be deployed over a 1,500 kilometer span? I think 14 terabits has been demonstrated by NTT. How close is that to the ultimate limit?
I mean, a lot of it will go back down to, you know, what's your span loss and things like that, because that all affects the signal to noise ratio and things. But I mean, certainly, yeah, if you do 2 bits per second per hertz, you can do 8 terabit per band, and kind of commercially available, certainly C-band, and people talk about L-band as well, although there's not so much of it deployed. So you'd have 16 terabits with that. If you wanted to do more than that, you know, now you're getting to some sort of 16 QAM or something like that, where, you know, you could potentially double that capacity once again up to 32 terabits, but then you would have a reach.
Doesn't that require improvements to signal to noise? You have to have launch power that's unrealistic?
Yeah. I mean, you get one thing when you go from PSK to QPSK, quadrature phase shift keying, you can double the capacity, and it doesn't actually hurt you in terms of signal to noise ratio. That kind of comes for free. But every time you go beyond that to more levels and the QAM constellation, if you like, now when you go to more and more levels, you basically trade off spectral efficiency for reach. So, you know, if you want to go to this higher spectral efficiency, you might have to do something a little bit cleverer in the optical line system. But then that means changing the infrastructure. So, you know, if you deploy more EDFAs, you reduce the amplifier space, and, you know, it kind of looks like a submarine system. Fair enough, then you've got better signal to noise ratio. Or you deploy some other techniques on the optical line system, like Raman amplifiers. They can also boost the optical signal to noise ratio. So, you know, if you want to go to those 1,500 kilometer reach and even higher spectral efficiency, you've really got to do something cleverer with the line system.
part of our perspective, though, is that spectral efficiency is an issue because you're limiting yourself to the C-band. If you can get yourself out of the C-band and open up the spectrum, then it matters less how efficient you are, at least for a given capacity level. So if you can get the S-band open, the O-band, the E-band, there's a bunch of bands here, then you can start buying capacity without having to increase dramatically spectral efficiency. And then if there are other approaches to modulation that have lower power, then that might equate to lower costs. So there's a very large number of factors that go into this equation.
Hello, yeah, Roque Aglianante. When you mentioned the bypass router model, you didn't mention the control plane, and specifically not GMPLS mentioned. So I wonder if that was on purpose or there's some development there too.
That was a time limit. Yeah. Go ahead.
I actually had a clarifying point I wanted to make about Drew's statement, or one of Drew's presentations. And I'll kind of preface this with, beware of transport vendors pitching ROADMs and optical transport control planes that automatically switch and do one for N protection, because what they don't understand is when neighbor adjacencies change and physical paths change, and what was the router ID 1 second ago is a new router ID now, is not protection. That's disruption. Be careful.
Yeah.
Transport people love that stuff. They don't understand control planes.
Well, there's a whole lot of work.
That's all.
Yeah. There's a whole lot of work that's gone on for a decade, probably. Well, not a decade, I guess, but 8 years on GMPLS control planes. And certainly major router vendors support GMPLS, but there's a whole lot more work to be done there. I didn't even put a single slide in, as you noted here, but I've gone to multi-day conferences solely on that.
Yeah, you wouldn't be on my panel if you did, sorry. Just teasing.